Alright, so this video is going to be part 12 of our sequences and series review. This video will be talking about Taylor and Maclaurin series. Okay, this is going to be the first of 2 videos on that. I'm just going to focus on another example problem in the next video. So, anyways, let's get started. So, when we were trying to find the Taylor and Maclaurin series, it was because we wanted to express more functions, a wider variety of functions, as power series, okay? We didn't want to just use this 1 over 1 minus something, okay? We didn't want to just use that, and that's why we're now going to widen our horizons to Taylor and Maclaurin series, okay? So to find the Taylor series, okay, we started off with our general power series, okay? The sum from n equals 0 to infinity of c sub n times x minus a to the nth power. Now what we did was we expressed c sub n in terms of our derivative, okay? And I did a long thing on that. If you want to see how we find that, you can just check out the explanation video on Taylor and Maclaurin series. But we ended up getting that our c sub n was equal to, let's see here, how can I represent this? Okay, the c sub n was equal to this nth derivative of f at a over n factorial. Okay, and that was multiplied by x minus a to the nth power. And this right here, this was the Taylor series. Okay, and how do you get the Maclaurin series from there? Well, the Maclaurin series is just a special case of the Taylor series when a is equal to 0. So if you wanted to find the Maclaurin series, I'll specify here that this is the Taylor series. The Maclaurin series, we're just going to have the sum from n equals 0 to infinity of, this will now be an nth derivative of f at 0 over n factorial times an x to the nth power. So the Maclaurin series is just a special case of the Taylor series when you have your a equal to 0. Okay? So now we're just going to talk about our 4-step process to figuring out a Taylor series, and then we'll do an example. Okay? So what was our 4-step process to finding a Taylor series? Well, the first thing we needed to do was we were given that function of x, and we wanted to take derivatives, okay? So we wanted to take derivatives of our function, okay? And we wanted to find patterns. And we wanted to find the nth derivative of f at x, okay? We wanted to write that down, and you'll see that in just a second when we do an example, okay? The second step of what we tried to do, okay, we wanted to plug in x equals a. And we wanted to find the nth derivative of f at a. Okay, the third step was just to set up our series. Okay, to set up our Taylor series. And then the fourth step is only if it really asks for it. All right, it's going to be most likely asked, okay, it'll be asked to find either the radius of convergence or the interval of convergence, or maybe both, but I have the fourth step as find the radius and the interval of convergence. Now, using this step-by-step process, let's do an actual example of this. So using this step-by-step process, let's find the Taylor series that represents the function natural log of x centered at a equals 1. All right, so the first thing that we need to do is to take derivatives of f of x. Okay, take derivatives of our natural log of x. We want to try to find some patterns, so let's do that. Okay, we obviously have that our f of x is natural log of x. Okay, and if we take some derivatives, we find that our f prime of x, well, that's equal to, we know that's 1 over x, right? But we are going to represent that as x to the negative 1. Okay? Now, here, there's a couple things that I'm going to be doing here to make the, because we want to find a pattern here. and I want to make the pattern as obvious as possible. So what I'm going to be doing is, well, we take our second derivative, this -1, I'm going to bring it down and just put it right here. Okay, I'm going to put it in parentheses here, and then I have an x to the -2. Okay, so I'm really going to make that -1 stand out. Okay, so whenever we have a negative term, I'm going to put that -1 right there. Okay, just a little something extra to help out here. Now, if I take another derivative here, f triple prime of x. Well, now this -2 comes down, cancels out that negative with on the 1, and now you just get a, well, this is going to be a 2 times the 1 that's already there, times x to the -3. Okay, and now you see I'm doing another thing, right? I'm not multiplying 2 and 1, because I'm making it obvious that this is 2 factorial. Okay, so there's another thing that I'm doing. Now, if I do the fourth derivative, this -3 is going to come down. This is going to be negative, right? Because this negative is coming down with the 3. So what I'm going to do is make this -1 times 3 times 2 times 1 times x to the -4. Okay, so not only have I outlined here, hey, we have a negative here, but I also outlined a 3 factorial, and then of course we have our x to the -4. Okay, so you know, it's these kind of things that just make the pattern a lot more clear. This -4 comes down, and it's going to get rid of that negative on the 1, so you have 4 times 3 times 2 times 1 times x to the -5. Okay, so you have a 4 factorial times x to the -5. Now, let's do the nth derivative of x. Okay, let's see what kind of pattern we got going on here. Now, you'll see that the negatives are alternating. Okay, just starting off with the negatives here. The negatives are alternating, but why is there not a negative on this natural log of x? That doesn't really make too much sense. Well, if you look at the natural log of x, you're going to notice that the pattern really isn't there at all. There's nothing really saying that this is part of our pattern that we see below here from the first derivative and beyond. So we're not even going to worry about natural log of x, okay? That's not going to be something that even matters with our nth derivative, okay? We're only going to care about our pattern. So we see that we have alternating -1s here, okay? And so we know that our nth derivative will have a -1. But to what power? Will it be to the nth power or to the n-1 power? Well, you see that, well, this f of x, that's going to be the n equals 0 term. Okay, that's where that goes. Okay, the f prime is going to go in the n equals 1 term. The n equals 2 term has the f double prime. N equals 3 will have f triple prime. Okay, and so on. You'll have n equals 4 and n equals 5. Okay, that's all in your Taylor polynomials when you actually expand out and write out your terms for your Taylor series. Okay, you'll see that. So if you don't really understand exactly what I'm saying, write out the first few terms of the Taylor series, and you'll see that the n equals 0 term has f of x, the n equals 1 term has f prime, okay, and so on and so forth. So what this means is that, well, we have our even n's, okay, that's the one that has the negative, okay. So if we want to make all of our even terms negative, we have to put an n-1 here. Now next we need to, let's look at the factorial, okay. Well, you see here that for our third derivative we have a 2 factorial. For our fourth derivative we have a 3 factorial. For the fifth derivative we have a 4 factorial, okay. So the factorial that we're getting is always 1 less than our derivative, okay. So the fifth derivative, right, is going to be a 4 factorial. The fourth derivative will be a 3 factorial, right, it's 1 less. So the nth derivative will be an n-1 factorial, right, 1 less. Okay, now you can still see that this is going to stay consistent for the second derivative and the first derivative. Okay, you'll still see that pattern because both 0 factorial and 1 factorial are both 1. Okay, so that still will, I mean, you can pull that out. You can say, okay, well, this is a x to the -1 times a 0 factorial. This is a 1 factorial here. You know, like, you can say that because it's not going to change anything. All right. So, anyways, now we got that. The last thing we need to look at is the x to the power. Okay. Now, you'll see that x is always being raised to a negative power. Okay, so we're going to have x to the negative something. Now, will it be like an n minus 1? What will it be? Well, for our first derivative, we have a negative 1. For our second derivative, negative 2. For our third derivative, negative 3. Okay, you can kind of see where I'm going here. For the nth derivative, we'll have negative n. And that is your nth derivative. So that's step 1. Now on to step 2. We're going to plug in x equals a. Okay, so let's plug in x equals a. And we're going to try to find the nth derivative of f at a. So let's start. We have f of, well, our a is 1, right? So we're going to plug in that for x. So we have f of 1. F of 1, but it means natural log of 1, and that's 0. Okay? So you can see that it actually, and you'll see this in a second here, this term doesn't even matter anyway, this natural log of x, okay? So we can actually just eliminate this from our series in general and start it from n equals 1, okay? Because if this is just 0, it's going to make that whole term 0, and you'll see that in a second here. I'll show you that when we write our actual series out in step 3. F prime of 1, well, in x to the negative 1, remember we're plugging in 1 for x, so x to the negative any of these guys is just still going to be 1, because anything, or 1 to any power is just going to be 1. Now f double prime of 1, you're going to get a negative 1 times 1. F triple prime of 1, you're going to get a just 2 times 1. The fourth derivative gives you a negative 3 factorial times 1, which is a negative 6. For your fifth derivative, you get a 4 factorial times 1, so that's going to be 24. And for your nth derivative of f at 1, well, if you plug in a 1 for this x here, you're just going to get 1. So you just have this left over, this negative 1 to the n minus 1 times n minus 1 factorial. And this is what we're going to be plugging in to set up our series. Okay, that's why we go through steps 1 and 2, so we can plug in this nth derivative of f at our a into our series. Now we know that this is the general form for a Taylor series, okay? Now our a is equal to 1, so we can just kind of get rid of these a's and put in 1's, okay? So this is basically the form that we're going to have our Taylor series in, okay? Now remember what I said. We are going to want our n equal to 1 here and not 0. Why is that? Well, because you see here for our first term, okay, for our first term, we're going to have the nth derivative, or not the nth derivative. Our n is going to equal 0. Okay, so we're going to have the 0 derivative, which means we're not taking a derivative, okay, of 1, so it's just f of 1. And it's going to be over, n factorial times x minus 1 to the n, and all that doesn't matter because f of 1 is 0. So that makes the whole first term 0. We don't even need to worry about it. Okay, so we're going to start this series from n equals 1. Okay, that's the first term that matters. So we have, anyways, the nth derivative of f at 1, which we know to be negative 1 to the n minus 1 times n minus 1 factorial. So we write the sum from n equals 1 to infinity of just that. And then we'll put it over n factorial and times x minus 1 to the nth power. Okay, so now that we've done that, I can erase this down here. All right, and now we can simplify this a little bit more. First, I mean, we know that this n factorial, that's the same thing as saying a n times n minus 1 factorial. Okay, so that means we can cross out these n minus 1 factorials, and we're left with a negative 1 to the n minus 1. That will be over n, and then this will be multiplied by x minus 1 to the nth power. Now you can actually see here, which is interesting, if you were to start listing out these terms, you wouldn't even be able to start from n equals 0 anyway, because look at this n, okay? that n, that's in the denominator, so if you had your n equals 0 term, you're going to get something undefined, right? So that wouldn't work anyway. We have to start from n equals 1. So now we have, right here, we have our series, okay? And the last step is to find the radius and the interval of convergence. So we're going to need to use the ratio test, okay? We're going to use the ratio test to see for what values of x is this thing going to converge, okay? So we take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Now our a sub n plus 1, that is just, well, first off, before we even start that, we don't need to include this negative 1 to the n minus 1, okay, or anything like that. That's just going to get canceled out with our absolute value, so no sense in including it. Okay, so let's just worry about this x minus 1 to the n over n. Now, remember, we have a sub n plus 1 over a sub n, so a sub n plus 1 will just be plugging in an n plus 1 for an n, and we get this, right? And then we're going to put that over a x minus 1 to the n over n, right? Just a regular a sub n. Now let's clean this up a little bit. This was looking pretty ugly at this point. We're going to have the limit as n approaches infinity of the absolute value of, we'll have a x minus 1 to the n plus 1 over x minus 1 to the n, and that will be multiplied by, we're going to have a n over n plus 1. Okay, the n over n plus 1, well, you know, we know that we can take the limit of each of these separately. So the n over n plus 1, we know the limit of that is just going to be 1, all right? So we can get rid of that. We don't need that anymore. Not important. And we now have this x minus 1 to the n plus 1 over x minus 1 to the nth power, okay? When we divide that out, we have to subtract the exponents, and we see that that's just going to be x minus 1. So we end up getting the absolute value of x minus 1. Now, for this to be convergent, this needs to be less than 1. Okay, for the series to be convergent, it has to be less than 1. That's what the ratio test says. So we can say that now x minus 1 is going to be less than 1 and greater than negative 1. All right, and that, let's get rid of the absolute value sign, and we can add 1 on both sides, or on all sides, I guess. To get 0 is going to be in between, or sorry, x is going to be in between 0 and 2. Okay, so that's going to be our starting interval right there. But we will need to test the endpoints, okay, because we need to see what happens when you have your x minus 1 with the absolute value around it equal to 1. Okay, that's what happens at 0. That's what happens at 2. Okay, you do 0 minus 1, you're going to get a negative 1, and that absolute value that's going to be 1, right? So this 0 and 2 make the ratio test inconclusive, and that's why we're checking the endpoints. Now the first endpoint we're going to plug in here, we're just going to plug in 0, right? So doing that, we still have our negative 1 to the n minus 1, and that's going to be over n. And then here, we're going to have a 0 minus 1 to the nth power, right? We'll have a 0 minus 1 to the nth power. Now that is the same exact thing as saying negative 1 to the nth power. Now you can do one of two things here, okay? You can multiply this negative 1 through here, right? You can multiply the two negative 1s together, and you'll get negative 1 to the 2n minus 1, okay? So that's perfectly fine to do. We'll do that right here. The sum from n equals 1 to infinity of negative 1 to the 2n minus 1 over n. Okay, that's something you can do. And then you realize, okay, well, this is making it so it doesn't matter what n I put in, I'm going to get an odd number in the exponent. Okay, 2n is going to make it an even number, and you subtract 1, it's going to always make it an odd number. Okay, so you'll always have something negative on top. The second way you can kind of think about this is that, well, I have a negative 1 to the nth power. What that does is it makes every single odd term negative. But a negative 1 to the n minus 1 is going to make every single even term negative. So these two together make every single term negative. That's what you can kind of think about it like. I mean, it's up to you. So this negative 1 to the 2n minus 1 is basically the same thing as saying negative the sum, wow, that was really bad, negative the sum from n equals 1 to infinity of 1 over n. Okay, now I just pulled the negative out, that's why I have the negative there. Okay, and that's the harmonic series, okay, and that diverges. So we're not going to be including 0 as an endpoint. That's what that tells us. Okay, now let's go back and plug 2 into our x and see what happens. If we plug in 2 here, we get a 2 minus 1 to the n, which is just a 1 to the n, and that becomes meaningless. Okay, we don't care about this 1 to the n. 1 to any power, 1 to any n that we put in is just going to be 1. So we end up right now with the alternating harmonic series, okay, and that's really nice. We know that that converges by the alternating series test. Okay, and what that means is that we are going to include our 2 in our interval of convergence, and that's what this is. Okay, so here's your interval of convergence. As far as your radius goes, well, the way I would find the radius is now you have your interval from 0 to 2. Okay, so let's write that out here. Intervals from 0 to 2. You have your middle, that's the 1, that's the middle of your interval. The radius of your interval is the radius of convergence. So from here to here is a distance of 1. Okay, there's your radius. R equals 1. Okay, so there you go. Now, one other way you could have found the radius, and I'll mention this again, I always like to give you an extra way if I can, but when we had the absolute value of x minus, well, what do we have? X minus 1, and that was less than 1, okay? Your radius is still right here, okay? That is your radius of convergence, okay? But you need to make sure that you have that x minus a form and nothing else, okay? Because that's what will give you your radius. But I honestly, like I've said in past videos, I think it's better to find the radius this way, because then you're sure never to get it wrong. So I just wanted to make sure for any new viewers or anything like that, you guys understand that's why I find the radius of convergence in this way, is because it's pretty much foolproof. Okay, so yeah, that is going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.